discussing the details of implementation and the various data structures and algorithms involved in the making of our project, the Parallelized Image Search Engine by Team Tech Phoenix. There has been a rapid exponential leap in the growth of multimedia databases, chiefly those that are operated by large tech giants like Google, Yahoo, Bing, etc. And millions of images are being uploaded to social media websites each day, and it is really difficult to even get started on searching for a relevant image from these massive global archives. So our problem statement is to develop a fully functional parallelized image search engine in order to effectively reduce the time of querying potentially millions of images, which is a highly sought after, a very complex computer vision problem that the community faces as of today, and it is extremely taxing in itself. Our objectives include parallelizing the involved sequential approaches by making use of the multiple processors or the cores on the local machine, also by experimenting with different algorithms and data structures while still serving scalability, expandability, interoperability, and aggregation as our core design principles. For this purpose, we have chosen the ImageNet LSVR CA 2012 validation set for object detection around 50,000 images of varying sizes belonging to 1,000 different classes in order to demonstrate the working. The key features of our project include deep feature extraction, principal component analysis for feature reduction, serial and parallel implementations, approximate nearest search algorithms such as partitional hard clustering algorithms, and graphical approaches, including graph automation. So we are running our application on a Flask-based environment, which is basically a lightweight Python web framework wherein we could work with HTML, CSS, and JavaScript on the front end and Python on the back end. We've used deep learning and machine learning frameworks such as TensorFlow, Keras APIs, sklearn, and the VGG16 submodule of Keras. We have made use of the multiprocessing library majorly, NetworkX for managing and curating graphs, and other modules such as NumPy, SciPy, and Pillow, etc. So we performed the deep feature extraction using VGG16 model both serially and parallelly. It took about 6 hours for the serial implementation and about 1.5 hours for the parallel implementation. For extraction, VGG16 is a well-established object detection model. In fact, also considering how it achieved 92.7% test accuracy in the ImageNet challenge, that is the same dataset we're using right now, it was the first runner-up in that challenge. So we performed deep feature extraction on the first fully connected layer, or the last but one layer, not considering the softmax layer of 1,000 nodes, a total of 16 layers. So that's where the name came from, VGG16. So we've used the VGG16 module from Keras by downloading the model weights from the internet. So coming to how we did the pre-processing part, we followed the pre-processing, which is a typical procedure as mentioned in the Keras documentation, like resizing images, asserting to RGB, extracting the pixel array, expanding dimensions, subtracting the average pixel values, pre-processing the input, and again contracting the dimensions, and finally normalizing the feature vectors. A few challenges that we face are that the VGG feature extraction part is very slow, and even when you consider the actual model, it took about 2 to 3 weeks while being trained on NVIDIA Titan GPU. And also when the extraction is done, it's extremely immobile, it occupies a lot of space and is pretty inefficient. The feature vectors that were exported, that we all exported from these images, took about 800 MB of space. Also, there are about 138 million parameters in the model. That explains why it's pretty inefficient in terms of space and time. Also, in order to avoid and deal easily with the TensorFlow memory allocation issues, we migrated to Windows Subsystem for Linux, WSL in Ubuntu. So this is the analysis that we performed earlier for serial implementation and parallel implementation with varying core sizes of 2, 4, and 8 on 9 different images. We have averaged their times of execution and tabulated the same, and the same has been illustrated on the clustered bar chart. So the observation is that the time taken by server 4 or the server with 4 cores is the least on an average, followed by server 8 and then server 2 and finally the serial implementation. So clearly the implementation with 4 cores is performing pretty well. The one with 8 cores isn't ideal because the system is having 8 cores and obviously all the cores can be assigned to a single process. other applications are in use. So that's where the difference is arising. Else, it would have been a course first and followed by the rest. Since the square in Euclidean distance is computationally expensive, we decided to also check out the Manhattan distance, but surprisingly, there wasn't a noticeable difference using the same, except for a decrease in visual accuracy. So that could be because of the fact that we're using an optimized inbuilt implementation of NP line-out norm for Euclidean distance, and there isn't one for Manhattan distance, and it requires us to do some sort of vectorized list comprehension. We also tried SciPy spatial distance modules inbuilt function, but the time taken wasn't affected a lot. So we decided to stick with the Euclidean distance since it's better than the Manhattan distance in terms of visual accuracy. So we are running the serial implementation and the parallel implementation with two cores. We're running them at the same time. You can find the complete video in the video description below, and you can also use the link. So we are running the serial implementation on port 5000 and the parallel implementation on port 8000. And we will now upload an image, and we will find the relevant similar images to that particular image. Firstly, we're running the serial implementation, then we're running the parallel implementation, and we can see that the time taken by serial implementation is 19 seconds, whereas by the parallel implementation is 14 seconds. This is a variable, but then we can see that the parallel implementation performs much better than the serial implementation. So until now, we have seen the standard nearest search algorithms in which we are not even leaving a single image and we are traversing through every image in the database, but this is very time consuming. So we wanted to explore the approximate nearest search algorithms in which we are using specific algorithm knowledge in order to get the right and relevant images that we require. So a few of the techniques are locality sensitive hashing, space partitioning, clustering, and graph traversal, out of which we have really seen that clustering and graph traversal would really make a difference and are very fast in nature. They're very convenient to understand, but then it's very complex and complicated to implement them. So coming to graph traversal, we tried exploring different options such as Azure Cosmos DB, Gremlin API, but then this incurred costs, so that we didn't go with this. And then we tried looking into the standard data structure implementation, but then this had the issue of memory leak. So we tried going with the Network X Python module, which is a very good module in Python for curating and also creating and managing graphs. So we also went with the automated graphical approach because it's much better than manual approach, which is very taxing, and we could also go a long way with the automated approach. So we went with the partitional hard clustering algorithm, which is the k-means clustering for the clustering approach, which is a very standard machine learning algorithm. And we chose the number of clusters or k to be 1000 because as we know, there are 1000 classes in the ImageNet LSVRC 2012 validation data set. We perform principal component analysis in order to narrow down these huge feature vectors or by retaining the 100 most very important features or the components in these feature vectors. We performed k-means clustering on top of these reduced feature vectors, and then we exported the clusters. And the time it took for PC analysis is about 2 minutes, and for k-means it took about 45 minutes. And the approach that we used for clustering is that we computed the average distance of the first three images in every cluster that we have in all of these 1000 clusters. We sorted these distances and we selected the top four clusters with the lowest distance. And then we computed and sorted the distances from the top four of these cluster images that we just saw in a parallel fashion by using four servers. And then we return the distance and the image paths in order to display on the Jinja template as our output for the top 50 relevant images. So the approach that we followed in order to automate the graph is that if image A is related to image B, then even image B is related to image A. So we tried to represent this relation as an undirected edge or an undirected graphical edge between these two nodes or images. So since we're already having the clusters, we tried to make each of these clusters a fully connected graph because every image in the cluster is related to every other image in the cluster. So the number of connections within a given cluster, if the number of images in the cluster is n, is nc2, and the summation over this for all the 1000 clusters gave us about 13 lakh connections or edges. So after step one, what did we do is, since we're already having a fully connected individual clusters, and this is an incomplete graph because we cannot reach a point from any other point, it is not guaranteed. So we tried to make it a fully connected or a complete graph by joining or interconnecting the clusters within in between clusters. So we tried to iterate through all the possible combinations between any two clusters, and we took the five most closest distances and we connected these distances. And we did this for every possible combination of the 1,000 clusters that we have. And that the summation of all the edges in first step, second step, and one more edge that we added gave us about 38 lakh edge connections, and the number of nodes is 50,000, number of 50,000 images, and one dummy node that we have, which is node 0, so 50,001 nodes and 38 lakh edges. So the approach that we followed is we computed the average distance of the first three images in each cluster with the query image, and then we sorted these distances in ascending order, and we selected the topmost cluster index or the first index, and we performed the breadth first search traversal or level order traversal for the first image in this cluster, and then we computed and sorted the distances for level 1 and level 2 nodes from this first image of the cluster, and then we return the corresponding distances and the image paths to the Jinja template in order to display the output. So here is the updated computational time analysis of servers. The first thing, the most optimized one or the fastest one is the server graph optimized. Here we just did the exact same approach as discussed in the graph automation and the graphical approach. But then the only difference is we optimized the time by using extra space and storing all the BFS traversals in it. So graph optimized was the first one, and the server graph was the second most optimized one, followed by server cluster, server 4, server 8, server 2, and then the serial implementation. Our project prototype has a wide range of use cases. It can be used almost everywhere where computer vision technology can be used, like retrieval of images from medical literature, search engines, search lenses, similar product recommendations, visually similar image recognition, fashion apparel recommendations, astrophysics, and determining almost closely related astronomical bodies, and also in various computer vision applications like image processing, data storage, because we are basically storing all the images in the form of feature vectors, and we could really devise a way to make the data storage more optimal and efficient. And also in detecting and classifying objects like road signs and traffic lights, and also creating 3D maps and motion estimation as well. It could also be used in self-driving cars because self-driving cars take into perspective everything around them that is coming from the sensors or cameras. So our prototype can be used there as well. And it could also be used in plant disease detection, in X-ray analysis, CT and MRI scan analysis, in detecting defective objects or defective resources or products, in agriculture and retail and marketing. So it has a number of use cases. So coming to the business model of our project, the business model is basically like a function of the project's value proposition, the market segment, the value chain, cost and profit, the value network, and the competitive strategy. We already know where our audience lie. They might lie in agriculture, retail, medical background, or even self-driving cars and various other categories. So we have a very decent market share, and we could create a lot of profit out of it by engaging better customers and bringing in better customers and utilizing our products or services that utilize this extensible prototype. And we could also like reduce the competition by making our product even more better by investigating and researching on enhancing and this enhancing the speed and even the time and space complexities of our prototype. Finally, coming to the achievements, conclusion, future scope, the prototype is a lightweight and extensible architectural framework. It has great visual accuracy. The proposed architectural prototype satisfies the pre-stated and the pre-initially thought of objectives. And we can see a noticeable time difference in between the serial and the parallel implementations. And we've also optimized the existing architecture, the standard nearest neighbor approaches, by clustering and graphical approaches, which are approximate nearest neighbor approaches, which created a big difference in time complexities. And we have also seen Euclidean and Manhattan distance, and we have seen how they make a big difference in the prototype and in the working of the model. Coming to the future scope, we can develop a prototype that works on a billion scale. So we can extend the same architecture to a billion scale. And we can also work and develop on the other approximate nearest neighbor search algorithms, and this would require a little bit of research. And we could also optimize the graphical approach even more further to make the performance even better. And we could also utilize the cloud compute services like AWS or even Azure services to use the cloud technology instead of like local infrastructure. And we can also extend the prototype to distributed systems, Hadoop, and cluster or grid programming systems. Hope you received great insights on the background, implementation, use cases about our project. Thank you for your time and have a great day.